Solubility. Do you remember studying the solubility rules? Right? We tried to predict whether a compound was going to be soluble or not, or whether it was going to be insoluble. And if we said it was insoluble, that meant that it was supposed to form a precipitate. Okay? So what we are working with today is the majority of compounds in the world, man. Not everything is completely soluble. It only dissolves a small amount. You could be a drug manufacturer, and just how much of your compound is soluble in the blood, right? On the opposite end of the spectrum, you have things that are they won't mix at all. They're not soluble at all in each other. And that's how a lava lamp works, right? It's because these foods are soluble in your mouth that you can taste them. And so you have taste buds all over your tongue, but it's not just taste buds that do the job of tasting, right? They work in conjunction with your nose, your olfactory cells. So if you don't like the taste of something, just close your nose. That'll help. So here's a table. I don't know if you recognize any of these compounds, but they are all insoluble according to the solubility rules. So they would all look like this. You'd put some of it in water and just wait a long time, and you end up with a saturated solution. The water is holding as much dissolved solid as it can. And in some cases it's hardly anything, other cases it's a little bit more. But our problem today is to predict just what is the concentration of the solid that dissolved. We're going to call that solubility. So what is the concentration of the solid in this water? The same thing as saying, what is the solubility of this solid in that water? So we're going to use this table to arrive at those answers. And we need an equilibrium constant. There it is, KSP. SP stands for solubility product. And since it's a special equilibrium constant, has a subscript, there's going to be a certain way that we have to write the reaction that corresponds with each of these equilibrium constants. And we'll talk about that. But let's just play around with this a little bit. Which compound in the table dissolves the most in water? In other words, it's the most soluble. So what we're going to look for is the biggest solubility product. So we have, here's a 10 to the negative 3. Is there anything bigger than that? I don't think so. So silver acetate is the most soluble, okay? And what's the concentration of silver acetate that would dissolve in water? That's solubility, and that's what we're going to work on. Okay, so what is the special way that you write a solubility or KSP reaction? The convention is the solid always goes to its ions. So the solid is always on the reactant side, and the ions it breaks up into is on the product side. So here's a solid. Let's go ahead and write the KSP reaction. So the solid goes on the reactant side, and the ions go on the product side. Now remember the trick to doing this? If you don't have all your charges memorized, just remember the 2 goes up there and the 3 goes there. Cation is always on the left-hand side, anion on the right. So that's going to be a positive 3 and a negative 2. So we'll have X positive 3 and Y negative 2, right? 2 goes up there, the 3 goes up there. Now how many of these things? That's the subscript. We actually have 2 X's and 3 Y's. 2 X's and 3 Y's. Barium phosphate is slightly soluble in water. Write its solubility reaction. So go ahead. Write the solid on the reactant side, ions on the product side. Barium phosphate goes to its ions. Barium, notice it has a +2 charge. And phosphate, and notice it has a -3 charge. And how many? 3 bariums, 2 phosphates. Write the equilibrium constant, the KSP expression for the reaction. So products over reactants. KSP equals products over reactants. So that barium concentration has to be cubed. Phosphate has to be squared all over 1, right? Because it's solid. How can the solubility for any solid in water be calculated? So solubility is just another term for, okay, what's the concentration of the solid in the water, right? We've left the solid for a long time in that water. What's its concentration? Just how much of it actually dissolved? What's our game plan? Just remember this. Solubility is the same as X in ice. So solubility is X in ice. So if you're going to do ice, you need a reaction. We're going to write the KSP reaction. And we want all units in our ice table to be in units of concentration. And things are going to work out great. Okay, so let's try this. Find the solubility of calcium fluoride in water. And remember, solubility is just the X in ice. So let's write our KSP reaction and then do ice. So solids go to their ions. Ca plus 2 and 2 fluoride anions. We've got our ice table. Solid, that remember that never shows up in KSP expressions, so dashes all the way down. We don't have anything there initially, right? Because we're just dumping calcium fluoride in water. X and 2x. X and 2x, right? Positive for products. So our KSP is 3.4 times 10 to the negative 11, and that has to equal the concentration of calcium times the concentration of fluoride squared divided by 1. Well, according to our ice table, 3.4 times 10 to the negative 11, the calcium is just X, the fluoride is 2X, but don't forget to square it. So I end up with 4x squared times x, 4x cubed has to equal 3.4 times 10 to the negative 11. So what's my x? 2.04 times 10 to the negative 4. Okay, now my KSP is a concentration table, so that's big M. And I can put more units on it, calcium fluoride. So my X in ice is 2.04 times 10 to the negative 4 molar calcium fluoride. That's the solubility. Now they want us to just use different units in B here. Find the solubility of calcium fluoride in water, but in units of grams per liter. So we already found it in molar, so let's just do some converting. We're going to have 2.04 times 10 to the negative 4 moles of calcium fluoride per liter. So just take it times the molar mass. And a mole of calcium fluoride, I have how many grams of calcium fluoride? Well, calcium is 40.078 plus fluorine is about 19 times 2, about 78.1. Okay, top multiply, bottom divide. 2.04 times 10 to the negative 4 times 78.1, about 1.59 times 10 to the negative 2 grams of calcium fluoride per liter of solution. find the solubility of calcium fluoride in 0.1 molar sodium fluoride in units of grams per liter. Okay. Do you recognize this type of problem? They're never going to tell you this, but it's a common ion effect problem. Right? When we see these compounds, we're not supposed to look at the alkali metal because they do nothing. Their sole purpose is to get the fluoride in water, right? Get the fluoride in solution. So now we have fluoride there initially. We have something to put in the initial row. So they want us to find solubility. So find X in ice of the KSP reaction for calcium fluoride. We just have a complicating factor here, and that's to put something in the initial row. No big deal. Let's try it. Calcium fluoride. A KSP reaction is calcium ion and 2 fluorides. Okay. Now let's make our ice table. Remember, solids never show up in equilibrium constant expressions. We have nothing there initially for calcium, but for fluoride we do. We have 0.1 molar. Exactly what this says. 0.1 molar. Change row, X and 2X. So at equilibrium concentrations, X for calcium and 0.1 plus 2X for the fluoride concentration. So my KSP is going to equal, what was it again? 3.4 times 10 to the negative 11 is KSP. 3.4 times 10 to the negative 11 has to equal products over reactants. X times 0.1 plus 2X, quantity squared, over 1. Okay? Now remember our story here. This exponent is awesome. 10 to the negative 11. It is very, very small. So that means we should have very little product, right? Because equilibrium constants are products over reactants. It's a very small number. So we have very small amount of product. This X is going to be extremely small. We're not going to hardly get anything. So you take something extremely small plus 0.1, you get 0.1 again. Awesome. It's going to be approximately X times 0.1. Don't forget to square it though. Over 1. So let's take my 3.4 times 10 to the negative 11, divide it by 0.1 squared. You get about 3.4 times 10 to the negative 9. Molar calcium fluoride. Now, did they want the answer in molar? No. Grams per liter. So let's do our converting. Remember, our molar mass was 78.1. So 3.4 times 10 to the negative 9 moles of calcium fluoride per liter. That's my solubility. Take it times the molar mass. On a mole of calcium fluoride, I have 78.1 grams of calcium fluoride. 3.4 times 10 to the negative 9 times 78.1, about 2.7 times 10 to the negative 7. Grams of calcium fluoride per liter. Okay. Now, do you remember Le Chatelier? He said that, right, if you add a common ion, equilibrium should shift in that direction. Since we have a common ion, right, the equilibrium shifts in the opposite direction. It should be really tough to dissolve this. It's going to shift towards the reactant side, shift towards the solid. So with no sodium fluoride, our solubility was 10 to the negative 2. Adding sodium fluoride, 10 to the negative 7. So much, much less calcium fluoride dissolves in the presence of fluoride because of the common ion effect, Le Chatelier's principle. The solubility of magnesium oxalate in water is 0.0093 moles per liter. Calculate KSP. Okay, this one's a little bit different. They are not asking for solubility, so we're not doing the whole X and ice thing. In fact, they told us what X is, right? They told us that's the solubility. So this has to be X. That has to be the X in ice of our KSP reaction, right? It has to be, because they told us. Remember, solubility is X in ice. So solubility is 0.093. So let's go ahead and make our ice table with X's in it, substitute in the KSP expression, and then just put in 0.0093 for X and calculate KSP. So try it. Magnesium oxalate, solid, goes to its ions. Magnesium ion and the oxalate anion. Make an ice table. Dashes for solid, nothing there initially. X, X. So my KSP is going to be products over reactants, right? X times X divided by 1. And we know what X is. So go ahead and substitute. My KSP is going to be X squared. 0.0093 squared, or just write it twice. And I'll have my KSP, 0.0093 squared, about 8.6 times 10 to the negative 5. The solubility of silver bromate in water is 0.0072 grams per liter. Calculate KSP. So do you see what to do here? Again, they told us what X is. It's just in the wrong units. We need to get that X into moles per liter and then substitute it into our KSP expression, just like we did in the last one, and we can calculate KSP. So let's get it into the right units. 0.0072 grams of silver bromate. So how many grams of silver bromate do I have in a mole? Silver is 196.6 plus bromine 79.5 plus 3 times 16 for the oxygen, about 324.1 is the molar mass. So 0.0072 divided by 324.1, about 2.22 times 10 to the negative 5. There's my X in the right units. So let's go ahead and make our You might be able to skip this part if you can see how to write the KSP expression, but if you can't, just go ahead and write it out. It doesn't take that long. Make a quick little ice table. Solids always dashes, nothing there initially. X's for products. So our KSP is going to be the concentration of silver ion times the concentration of bromate, which is just going to be X times X divided by 1. So that's going to be 2.22 times 10 to the negative 5, but squared. About 4.93 times 10 to the negative 10. What is the solubility of lead fluoride in water? And they give us the KSP. Recognize what to do? They want to know what solubility is, so find the X in ice of our KSP reaction. Okay, I think it sometimes helps to write the entire KSP expression. Otherwise, I very often forget to do this squaring part. So maybe you do too, so it doesn't take very long. So I think it saves time in the long run. So my KSP is 2.7 times 10 to the negative 8. That has to equal the concentration of my lead, which is X, the concentration of my fluoride, which is 2X, that has to be squared. That's going to be 4X cubed. So 2.7 times 10 to the negative 8 divided by 4 equals cube root 1.89 times 10 to the negative 3. Molar lead fluoride. And you notice they didn't care the units, so I'm just going to leave it there. Okay, so the idea here is we have a lot of insoluble solids. And our goal here is to predict the solubility. What is the concentration of this solid that actually is present in a saturated solution of water containing this solid? And the answer is, write the KSP reaction, make an ice table, and solubility is the X in ice.